Here we're discussing about the Compton effect, which demonstrates both the quantization of energy and momentum. So this is about scattering of a photon by an electron and is like a particle-particle scattering. Arthur Compton was an American physicist and did a series of experiments with X-rays and finally came to the conclusion that interaction between X-rays and electrons can be explained only if X-rays are treated in some way as particles. When a photon hits an electron which is initially at rest, a part of its energy is transferred to the electron. The electron gains energy and momentum and moves off at an angle. The photon also loses energy and momentum and moves off at a different angle. And the conservation laws control the whole story. The experimental finding is termed as Compton Effect, and he received the Nobel Prize in Physics in the year 1927 for this work. Now let's see what this Compton Effect is all about. Let's now try to visualize the Compton effect, which is the interaction between an incident photon and a target electron at rest. Here, incident photon is represented in yellow line and target electron is at rest. You can see that after the collision between the two, the incident photon is now moving at a different direction, say phi with the reference line, that is a scattered photon, and this target electron which was initially at rest, it has now started moving in a particular direction, say theta with the reference. So this is the scenario of the interaction between incident photon and the target electron. Now energy and momentum are conserved in such an event, and now we'll try to write what is the energy of the incident photon and target electron before and after collision, so that we can apply the laws of conservation of energy and momentum to find out about the Compton effect. So we'll begin with the incident photon. You know that photon is a massless particle, so we have the energy of a particle is given by the equation root of m square c raised to 4 plus p square c square. And since photon is a massless particle, here m will be 0. Therefore, energy will be given by, for a particle which is massless, that is photon, energy will be given by root of p square c square alone, because m equal to 0. Therefore, root of p square c square, it is pc. So E equal to pc applies for photon. So P can be written, momentum can be written as E by C. Remember, this is only for a massless particle. So that is, for example, photon. So here momentum of this particle will be given by E by C. And what is the energy of a photon? You know it already, it is h nu. So h nu by C will give the momentum of the photon. Therefore, energy is h nu. So we got both what is the momentum as well as the energy of this incident photon. Now what about the target electron? Since the electron is at rest, we can directly write the momentum of this electron to be 0, because it is at rest. And what is the energy of an electron? Energy of the electron is given by mc square, and that again follows from the expression E equal to root of m square c square plus p square c square. Here p is 0, so we get E equal to root of m square c raised to 4, which is m c square. So the energy and momentum before collision we got. Now what is the energy and momentum after collision? You can see that the photon has lost some energy in the process, and therefore its frequency may be different and its energy may also be different. So let's take that energy to be, let it be h nu prime. Nu prime indicates a change in the frequency. Therefore momentum is given by E by C as before. So that is H nu prime by C. Moving on to the scattered electron. The electron, which was initially at rest, has now started moving. You can see that angle that it moves is taken to be theta with respect to our reference. So it has got a momentum now. So let's take that momentum to be P, and energy of a moving electron is given by the expression root of m square c raised to 4 plus p square c square. So this is a scenario of the Compton effect, that is the collision between a photon and an electron which is at rest. So before collision and after collision we have written the energy and momentum for both incident photon and the target electron. So Compton effect is like a collision between a photon and electron as if both were billiard balls. Now we'll try to draw the vector diagram of the momenta and their components of both the incident and the scattered photon as well as the scattered electron. So for that, first let's draw the uh, vector diagram or vector diagram of the momenta for the photon. The momenta of photon was given by h nu prime by c, and we have taken the scattered photon was in the angle phi. So resolving this into the components, we can write the horizontal component to be h nu prime by c cos phi along the phi direction, and perpendicular component will be given by h nu prime by c sin phi. Okay, so I think that's clear. We have resolved the components of the momenta both in the perpendicular and the parallel direction. Now moving on to the electron. In the similar fashion we can resolve the momentum components, because momentum we have taken the scattered electron has a momentum that's given by p, because initial momentum was 0. The aftermath momentum we are taking to be p, and that has happened at an angle, it's moving at an angle say theta with the reference. So we can resolve this component again in the horizontal as well as the vertical direction. So the horizontal component will be p cos theta, that's along the angle, and this component will be, the perpendicular component will be p sin theta. So we have taken the vector diagram of the momenta and their components. This is done because we are going to do the conservation of both momentum and energy to arrive at the Compton effect. So in order to equate, we need the components in the x as well as in the y direction. So that is why we have taken the momenta and the components of the incident and scattered photon as well as the scattered electron. So momentum, unlike energy, that's a vector quantity and has both direction as well as magnitude. So in the collision, momentum must be conserved in each of the two perpendicular directions. So here let's now apply the conservation law of momentum. We may write the equation: before collision, initial momentum must be equal to uh, the final momentum. So we have to find out the initial momentum and then look at the final momentum and try to equate. So if you take the initial momentum, we had initially a photon moving, having a momentum h nu by c, and the electron was at rest, so its momentum is 0. So that must be equal to the final momentum. Final momentum we are taking here, this is because we had components both x direction and the y direction, we have to first go for the x direction, or in the x-axis, or you can say in the original photon direction. So h nu by c plus 0 is in the x direction, and the after collision momentum in the x direction will be h nu prime by c cos phi plus p cos theta. Let this be equation number 1. And then we go to the perpendicular direction or the y direction, and you can see the initial momentum in the y direction initially was 0 because we had collision only in the x direction. So initial momentum is 0. Final momentum is h nu prime by c cos phi, sin phi minus p sin theta. Here minus have come because the directions are opposite. So this is the conservation of momentum formula. Now we are going to rearrange equation 1 and 2 and get a meaningful result. So you may multiply equation 1 with c throughout and get an equation like this: pc cos theta is equal to h nu minus h nu prime cos phi. Call that equation number 3a. Similarly, equation 2 also we may multiply it with c and get an equation of form pc sin theta is equal to h nu prime by c sin phi. Let that be equation 3b. Is square 3a and 3b and then add. So 3a square plus 3b square will give us, you can see that left hand side is pc cos theta and pc sin theta, which on squaring we get p square c square cos square theta plus sin square theta. So you know that cos square theta plus sin square theta is 1. So left hand side will be p square c square, and right hand side is h nu the whole square minus 2 h nu into h nu prime cos phi plus h nu prime the whole square. Call that equation number 4. Just square and add and use the identity sin square theta plus cos square theta equal to 1, and on the right side it will be sin square phi plus cos square phi is equal to 1, and you will arrive at this relation. Now moving on to writing the equating the two expression for total energy of a particle, we have the equation for energies, that is energy is given by, you know, it is given by kinetic energy plus the rest energy, which is mc square. Also energy is given by the expression root of m square c raised to 4 plus p square c square. Let this be 5b. Now equating the two, we get kinetic energy plus mc square the whole square will be, I have also squared the expression, so m square c raised to 4 plus p square c square. The square root disappears because we have squared. So that implies you can expand the same and get the expression as kinetic energy square plus 2 into kinetic energy into mc square plus m square c raised to 4 will be given by p square c square plus m square c raised to 4. Now we may cancel m square c raised to 4 here, and here also there is an m square c raised to 4, and we finally get the expression relating p square c square. So just rearranging, p square c square is given by kinetic energy square plus 2 times kinetic energy into m c square. Let this be equation number 6. Now what is kinetic energy here? That is what we have to find out. So you can see that the whole collision process, initial frequency was nu for the incident photon, scattered photon has a frequency nu prime. So this change in photon energy from, or photon frequency from nu to nu prime, that will be the gain in electron kinetic energy, because an electron was at rest, but after collision the electron has started moving. So where does it get its energy from? It must be from the energy that is lost by the photon. So we can write an expression uh, relating the loss in photon energy equating to gain in the kinetic energy of electron. That is, loss in photon energy will be equal to the gain in electron energy. So the gain in electron energy is actually its kinetic energy, because it has started moving. So loss in photon energy, we can write initial energy is h nu and final energy is h nu prime. That must be equal to the kinetic energy. Let this be equation number 7. So we got the expression for kinetic energy, which can be substituted back into equation 6. So substituting equation 7 into the equation 6, we get p square c square is equal to kinetic energy the square, that is h nu minus h nu prime the whole square, plus 2 into h nu minus h nu prime into m c square. So we have nu by c into nu prime by c into 1 minus cos phi, that's equal to mc by h into nu minus nu prime. So we may use now the expression nu nu is equal to, or we may write nu by c as 1 by lambda, or nu equal to c by lambda. Likewise, nu prime by c will be the corresponding wavelength, that is 1 by lambda prime. So use that expression, nu by c is equal to 1 by lambda and nu prime by c equal to 1 by lambda prime, and we get the expression as before expression, mc by h into 1 by lambda minus 1 by lambda prime is equal to 1 minus cos phi by lambda into lambda prime. Equation 11. Now simplifying the expression in this bracket, we get mc by h into lambda prime minus lambda by lambda into lambda prime, that's equal to 1 minus cos phi by lambda into lambda prime. You can see lambda prime and lambda we can cancel from both the sides, and we are now trying to obtain an expression here, that is lambda prime minus lambda will be taking this h mc by h to the right hand side. We can write h by mc into 1 minus cos phi. That's equation 12 and the important result of the Compton effect. So this equation in fact gives us the Compton effect, which says about the change in wavelength. Remember, lambda means the initial wavelength and lambda prime is the initial wavelength of the photon, and lambda prime is the the wavelength of the photon after the collision. So we got lambda prime minus lambda, which can also be written as delta lambda. So this equation may be shortened as delta lambda, which is lambda prime minus lambda equal to h by mc into 1 minus cos phi. So this is equation 13 and represents the Compton effect. And here let's take this h by mc. You know that h by mc is a constant because h is a constant, m mass is a constant, c is another constant, speed of light, which is 3 into 10 raised to 8. So all this we may combine and get a value for this h by mc, that is approximately it comes to be 2.426 into 10 raised to minus 12 meter, or that is 2.426 picometer. Picometer stands for 1 into 10 raised to minus 12 meter, and so this constant we are calling it as lambda c. Okay, let that constant be lambda c, which is known as the Compton wavelength. And that is a constant. So finally, we may write delta lambda to be lambda c into 1 minus cos phi, equation number 14. And this is the shortest expression that we can remember for the Compton effect, or this is represented by the Compton effect is represented by this equation we can see. Now we have to find out what is the implication of this expression and what is Compton effect actually telling us.